All right, so hello everyone. Thank you for joining and welcome to today's webinar presented by AMPL Optimization on how optimization generates millions, cases from energy, transportation, supply chain, and finance. Your presenters are Bob Foer, President and Co-founder at AMPL Optimization, and Filipe, Head of Development at AMPL Optimization. Bob is Professor Emeritus of Industrial Engineering and Management Sciences at Northwestern University and President and co-founder of AMPL Optimization. He has written extensively on optimization modeling and computation and has served as area editor of leading journals in this field. His work has been recognized by the Informs Impact Prize and by election as a Fellow of Informs. Filipe is head of development at AMPL Optimization, where he oversees and/or leads most software development projects. He has a PhD in computer science with a thesis on integer programming models for cutting and packaging problems, which are currently being used in industry worldwide. After the presentation, we will remain live for 15 minutes for questions. Feel free to submit questions via the Q&A function in Zoom, and we will ask them at the end of the presentation. And now with that, I will turn it over to Bob and Filipe.
Okay. Where is... Oops. Okay. All right. I'm just getting the share working here. There we go. Okay. All right. So thanks for attending this webinar. And Filipe and I will do the presentation. I will start out by giving a sort of set the scene with an overview of what's going on in AMPL and optimization. And then Filipe will get to the main part, which is the cases from all these areas. And being from AMPL, our examples will all come from the AMPL modeling language and system. However, I'd like to get started by taking a broader view to set the scene and look at where optimization is heading these days, and some technologies that are really important that'll figure in the later part of the examples. And so I'm going to do four quick slides about where optimization is headed in 4 respects, and then I'll describe what's new in 3 particular areas that are going to be important to the presentation of examples, and then Filipe will do the how optimization generates millions, the case studies in these major application areas. So let's get started here. AMPL is a modeling language. That is, it's a system for describing optimization problems to computers and for managing their use. And so the first question is where are modeling languages headed? And basically, they've always been headed in this direction, which is to describe optimization the way you think about it, like you describe it to the computer in ways that are natural to people who do these things. And it used to be that what didn't involve much. Mainly, you had linear. For example, you had linear programming kinds of systems, and all you needed were a couple of operators here and a couple of comparisons, and that was enough to describe all sorts of models. And in fact, they were called algebraic modeling languages because they had just this little algebra. Today, it's much different. And there are just all sorts of things that people use in describing optimization models, not only all kinds of algebra and functions, but various kinds of logic and other things as well. And so this has put a lot of pressure on modeling languages to keep up with this, to be able to be this rich. Okay, so to describe what people are thinking about. Now, modeling languages don't actually solve optimization problems. There are these number crunching solvers that do that, and there are many of them. And so next question I ask is where are solvers headed? And the answer is solvers have become more and more general. So one solver for everything means that your solver should handle all kinds of optimization problems. And that makes them very complicated. So a solver typically has one part of it that solves easy problems, okay? And for example, linear programs, and and does that with a fast and straightforward local search kind of method. But for all other kinds of problems, there's another part that handles them. So for anything that involves logic or integer variables or sort of non-convex functions, which is most kinds of functions, you have to do some sort of tree search. So there's this whole different part of it that does this branching tree. And at each node of the tree, it has to solve an each. So these two go together. And so this has become a big complicated thing. And it's also placed pressure on modeling languages because if they're going to handle, solvers are going to handle lots of kinds of problems, that means that it's becoming natural to write lots of kinds of expressions. And you need to be able to do that. So then, now, even if you have modeling languages and solvers, you need some way of taking the optimization application you've built and putting it inside a bigger system that is going to make it deployable. So the next question I have here is where deployment is headed. And the answer these days has been increasingly one word, Python. So Python applications are really the big thing right now. And for that reason, you can expect to have some desire to extract and process the data in Python, and then after the optimization is done, to display results and send them out as an application to be used. Okay? And so this has also created pressure on modeling languages. There are sort of now two kinds of modeling languages. There are ones that are sort of built inside Python. They're sort of made out of Python statements. And they're more like Python, which is good in a way, but they're less the way you think. On the other hand, there are modeling languages that are more the way you think, but they achieve that by not trying to be like Python. Okay? And AMPL is the second kind of language. So AMPL has advantages of giving a clear model description, keeping independence from data, and being able to generate problem instances much faster. And so what you're going to see in the examples is that there's an AMPL part and an amplpy part. And the AMPL part is the modeling language that describes the model cleanly, and hopefully the way you think about it. And there's an amplpy part, which is the Python library that enables you to use AMPL in applications. So one more slide here. And this is where everything is headed. And everybody knows already the answer to that. And so this has also made a big difference to modeling and optimization systems. First of all, you can create applications by making a request to a chatbot, and it will sort of start building what you need. And this applies both to building models with the AMPL stuff and programming deployments by writing amplpy code in Python. Okay? And another thing is that it's made it much easier to translate models. So you can take a model that was written in one modeling language and ask the chatbot to translate it into a different one. And so that you're not so stuck on one particular modeling system as it used to be. And so that's also been something that the modeling languages have had to adapt to. Okay, so those are my 4 opening slides, and now I'm going to talk about what's new in 3 important technical areas here. And let me start with automating model reformulations, and to explain that, I'd like to use an example. Okay, so here's a typical user question that comes from Stack Exchange, which is a website just for asking questions about mathematical and technical things. And the user basically says, how do I write the following condition in my model? If A greater than B, then C equals D, else C equals E. Okay? And so these questions are read by a lot of experts, and here's how an expert replied. Said, well, you have to add this 0, 1 variable delta, and then you can break it into this equivalence and these 2 implications. And now we take this equivalence and we rewrite it as in a linear form, and we take these and we rewrite it linearly. And now we have all these constraints which do the same thing, okay, in a way that now you can send it to a solver, because solver, it's the person was thinking in terms of linear programming solvers, right? And then further, it said many MIP solvers have indicator constraints. This can make things easier. And what the expert was saying there was that these are a special kind of implication where you have a 0, 1 variable equal 1 or 0 on the left. Those are called indicator constraints. Some solvers know what to do with these, and so you can just send it these. Other ones don't, and you have to send it what's down here at the bottom. Okay? Now, so that's the expert response. What happens if you take the view instead that you should describe it the way you think about it? Well, in AMPL, you just write it like this. A greater than B implies C equals D, else C equals Z. So expression is much simpler, but what happens when you try to use that? Okay, so I try to put this in my AMPL model, and using the older versions of solvers that we had, well, it either rejected this operator entirely, this implies operator, because it didn't know about it, or it said, well, I know that operator, but this is not an indicator constraint. Okay, and so well, I don't know what to do with it. Okay, and our goal was to make that not happen anymore. So newer versions, it just says optimal solution. And this high solver here does not have indicator constraints. The Gurobi solver does, but somehow that's all done automatically to figure out what's needed and what transformations should be done and so forth. All those transformations on the previous slide happen behind the scenes in AMPL's communication with the solver. And that's what we mean by automating model reformulations, that instead of all those reformulations described by the expert in response to the question, you just write it the way you think of it, and the reformulations are done automatically, okay? Whatever it is that the solver needs. So in general, the issue was AMPL has a rich variety of expressions, and each solver supports some of those, and the ones that it doesn't support or fully support have to be reformulated, okay? And what we did was, in order to implement that in an effective way, was to create a completely new general library for writing AMPL solver interfaces. And then using that library, many expressions can be supported with many solvers, taking advantage of whatever particular requirements the solver has and particular things that it supports. And as needed, the expressions that you write in your model are automatically reformulated. So that's the automated model reformulation. Basically, you don't worry about it. You let AMPL worry about it. And this new library was developed by Gleb Bailov, a member of the AMPL development team. And there's another slide I don't have time for, but I'll put it in the posted slides that give some references to that. It's an open source interface, so people can use it to add their own solvers. And here's one more page of all the supported forms. So you can see here that in addition to ones like this implies that you saw before, there are many other things that you can write that are recognized by AMPL and that can be translated appropriately by this new interface library. So and furthermore, they can all be used in combination. It's not just you can use one at a time. Okay? So quite complicated things can be expressed, and they will be translated using this library. Okay? So let me move on now to the second what's new, and this is just one slide. The big thing in new computer hardware is GPUs. GPUs are behind all the AI chatbots being able to process so quickly. And people have naturally asked, could it be used for optimization? And they developed new kinds of solvers that can work with them. It's still at a somewhat early stage, but there's things out there you can try. And so there's this CUPDLP-C library that's been integrated with a couple of solvers. And the problem with trying it out is that you really need a high-powered GPU card in your computer, which you probably don't have. But we've set it up so that in AMPL's online model collaboratory, you can get access to some machines that have these powerful GPUs, And so you can try it free with the free high solver, or get a trial with the commercial COP solver, and actually try it out for yourself. Meanwhile, NVIDIA, which is the biggest maker of GPUs, has come up with their own solver, and they're in the process of interfacing that to the AMPL library. So we expect to see that very shortly being available in some form for people to try as well. Okay. There's another kind of advanced processor that you hear about, which is quantum processors. And there are various quantum solvers that run on quantum hardware, or they're quantum inspired in some way. They run also on some regular hardware, or a mixture of the two. And as yet, these have been around for a while. They seem to get better every year, but as yet they're use fairly specialized hardware and software. So I'm not going to promise anything about those at this point. Now the third new thing is generating Python deployments. So I'm going to here again just give an example. I think that shows what's going on. So I'm going to take a simple portfolio optimization and showing how you'd generate it using AI. So what I want to do is get an initial AMPL model, add some constraints and improve the formulation, embed it in the amplpy so that it can be part of a larger system. Use some Python package to get some real data on the stocks in the portfolio. And then you use a different package to add interactivity and result display. Okay? And I'm going to do this using ChatGPT with just 7 requests, and eventually move it to various environments for testing and use. Okay? Now this is pure ChatGPT. This is not some special chat was specially trained on AMPL. This is just what you get out of the box. You can type exactly the same things and get similar results. Okay, so here's the 7 requests that I gave it. Okay, but I want to show you the results. So I'm going to get out of this now and go over to a different screen, and I'm going to share again. If it will. Oh, I have to unshare. Whoops. Can't start sharing till you stopped. Okay, there we go. Okay. And so you type something like this: write a portfolio optimization model in AMPL, minimizes risk subject to lower bound on return and a given total asset value in dollars. And you do that, and hopefully it won't flake out. There we go. And it writes you an AMPL model. There it is. And you can see there set some parameters. There's some variables, and subject to constraints, and minimizing variance. So and then it gives some sample data how to run it and so forth. And so it knows all about AMPL, and we didn't do anything special there. Now we might want to change it. So as I say, add a requirement that the number of different assets is bounded. And so, and now remembers my previous request, and it writes it all out again, and now it has some new variables. And it's defined some 0, 1 variables and some new constraints and so forth. And so you can gradually enrich it like that. Now, I don't want to make you sit here and watch all these things come out. So I've saved the previous session here. And the third thing I asked it was to remember I said there were all these new operators beside, they're more like logic operators. And this thing here used 0, 1 variables. I said, express the same model using AMPL's count operator instead of binary variables. And it said, okay. And you see now it says the count of assets such that there's a positive amount used is less than or equal to mass assets. So this is sort of, I would say, a more natural way of writing it. And as yet, it doesn't do that automatically, but if I ask it, it will do that. Yeah. Then I said, write an amplpy program that sets this up, make up test data of 10 assets, and set up to solve using Garobi. So now you see a Python program that imports amplpy and has the whole model inside it here. You can see the minimize and the subject to and so forth. And then it generates random data. Here it's sending the data to AMPL, and then it solves. And here it's just retrieving the data from AMPL. You can see get variable and displaying the results. So now I've made an amplpy program out of it. But now I want to be able to do it with real things. So I want to set me up with an example that shows how to use real stocks. So I say choose ticker symbols from 10 commonly traded tech stocks. Set the mean and variance values using the Python AVI of some public database. So it uses something called Y Finance and picks out 10 stocks for me. And now you see that it's importing this Y Finance here. And so I don't know how to use Y Finance, but this is something any programmer has discovered that you can get started with a package without knowing anything about it, because the ChatGPT will figure out how to use it. So this downloads all the proper mean and variance data for these stocks, and then goes through what was on the previous slide, and then displays the returns and so forth. So now at this point, I'd like to work with this that I've got. So I want to put it into a Python notebook. So I asked the chatbot to generate a file that contains the program and it places the model in its own cell, and it gives me this file back saying, okay, here's a file you can run that'll run it in a Jupyter notebook. And then it looks like this. So there's the Jupyter notebook. It's got the whole AMPL model, including the count operator, and it's got the whole thing that uses Y Finance to get the data, and generates the mean and variance and sends it all to AMPL, solves, and displays the results. So if I run this, the model runs really fast, and let's see. Oh, I have to do that. Okay, model runs really fast, and then this part runs, and you see that it's run Garobi. It's got a solution and displayed the portfolio. I had a limit of 5 assets, so it used 5 of the stocks that would give me the best, the minimal variance. So I can work with this, and if you want to improve the way it's working in Python, you can work in this notebook. The final thing I asked was, I go back to here, add calls to this program called Streamlit that'll provide sliders to set the parameters and display the optimal solution in a pie chart. Okay? And again, it gives me this Python program that I can run. And when I run that, I get this. And so here you see the 5 stocks and their amounts. And if I go here and say that it can use 6 stocks, then it reruns it, and you see it uses 6 of them, and it's put in another one here. And but if I say only 4, then it gives me a solution with 4 stocks. And I can do other things. You can see here that the return is already over 19%. So saying that the minimum return is 10% doesn't really say much. But if I put the minimum return up to 20%, then it'll change what it does here. And to get a 20% return with a little more variance. And so I can also quickly generate these kinds of things. So then, okay, so that's what I wanted to do in the way of introduction. And now I'm going to turn it over to Filipe, who's going to show the examples.
Sorry. So now I'm going to start presenting the applications where optimization really has massive impact. But before getting into that, I'm going to just quickly go over some of the key reasons why AMPL is used there for these applications where performance is so critical and the impact can be so massive. So just to give you an idea of the type of applications that I'm going to be talking about. So applications, for instance, in supply chain, here you can see a case study where the revenue was increased by 200 million. This is the baseline. So anything that I'm going to show you is going to be above this. So just to give you an idea in terms of where optimization really causes impact. And supply chain is quite big, but where it is really big for us, and I will say that the title is wrong. It should not be our optimization generates millions, is our optimization generates billions. And the applications is this one. It's going to also be the last one that I'm going to be mentioning, but just to give you a perspective of the ranges of the applications that we are talking about and the impacts in terms of revenue and the amount of money that can be generated with optimization. So I'm going to be talking about stuff that I hear from conversations with customers. So a lot of stuff under NDA. So the trick here is that I use AI tools to check if they are aware of some of this stuff, if they already know how people use optimization to predict energy prices, that kind of stuff. If they know, that is public domain, so I'm safe. So I'm going to mostly be showing things that AI tools already know. The only difference is that I know if they are lying or not, because I have seen this stuff being done in practice, but I just cannot really share the true details from our customers. Just to give a perspective of the industries where AMPL is used the most. So energy, finance, mining, telecommunications. So these are some of the main applications. And here in particular, in the finance, there is a lot in terms of commodities trading, because the same type of models that are like used to optimize an electric grid, gas pipelines, and so on, similar models can be built to then simulate under many different scenarios and in that way obtain some information, let's say energy prices. If you manage to predict energy prices for tomorrow, you can really make a ton of money. So that is the kind of stuff where optimization really takes you to another level in terms of revenue. There is also like airlines where optimization is critical and is essentially the entire business depending on it. And airlines simply cannot operate without really optimizing every single aspect of the business. So, and why AMPL is used for this? So AMPL allows you to express complex problems in a very simple way, like Bob mentioned before. So we have these automatic reformulations. This is from a real application. This is for a thermal battery. And if it is charging into consecutive time periods, we cannot change the charge rate by a lot. Since it is a thermal battery, we are essentially setting a temperature. And if we keep changing it a lot, it's not efficient. And in AMPL, you express this just like this. Otherwise, we'll need to use like tricks like big M and so on, and it is error prone. So if you are really managing like real equipment and so on, it is critical to be able to have a model that is clean, easy to validate, and correct. So AMPL gives you that. And of course, that is a very simple example, but this type of logic that often shows up in real models can get very, very complicated. Like all of these in this constraint is logic. And this is in fact an XOR. So, and we have the XOR operator. We could just have XOR here and just have this initial part. But linearizing this by n, it will be like 200 lines, like 200 constraint declarations. So very big and complicated, very easy to make mistakes. And other than this, so other than being able to write very complicated models efficiently, we also need to be able to efficiently generate these big models. So especially if we are going to be running tons of scenarios, we need to be able to build models with new data from scratch really, really fast. Here we have a benchmark that we really like to show, because we don't like to do our own benchmarks, because we could always like pick a toy example and just adjust it to be better than everything else. Here is someone that is trying to beat every other tool. So this is a modeling tool that was being created by a person. AMPL is down here, and here we have Pyomo, Here we have Plasma, here we have Jump. And these are this modeling system being used with 1 process, 2, 4, and 8, and trying to beat AMPL and essentially giving up. So you don't even need to read the paper. You can just go through the abstract, and here at the end, you can see that with parallel model generation, they managed to outperform Jump and getting close to AMPL, but that's it. That's what they managed for a specific type of problem. So not really general. And it is quite nice to see how hard it was for this person to beat us. Now, another thing, you have these models being generated really fast. Then we have MP that takes these high-level modeling constructs, sends them to different solvers in efficient ways. So model quality, that is also assured. And then you need access to all different solvers so that you can also see which solver works best for your problems. So that is what we provide. This is what we provide for linear and quadratic solvers, now also getting into the global space. So now we have Groby and Express. The type of applications that I am going to be talking about are applications where it's mostly for these top 3 solvers and also the most expensive ones. But as you are going to see, this is pocket change. The cost of these solvers are not going to be anything based on the type of returns of the applications that I will be mentioning. That is for linear quadratic. Here we have the nonlinear solvers, where right now we just have Baron with MP interface, so automatic reformulations. We are now going to very soon extend it to many of other of these solvers as well. So this is a very recent feature that should be released very soon. Now, just a little in terms of resources for AMPL and Python. So we have Colab, we have Mobook and Streamlit. I'm going to be using mostly Streamlit, where I keep going back to put additional examples. So every time I see some interesting application, I put a simple example similar to the real application, but without ever really sharing anything secret. And for you to try AMPL, you can also go to try.ampl.com and you get access to a notebook where you can see an energy model in AMPL, data being loaded. So it's a very quick way to learn how to use it. So very simple, you have your model, you have your data in Python, you just load the data, you solve using one solver, confirm that it is solved correctly, retrieve the results, and then some code just to display these nice charts. Okay, getting back into the presentation. Okay, so now how optimization really generates millions. So let's start with the supply chain. So for supply chain, we have been doing a course, a master class with Christina Radu, which is an expert in supply chain. And we have a Streamlit app. And for this app, one interesting thing is that a lot of the model itself was generated using AI. So I was getting this from Christina, and from this I was then producing the declarations in Chat GPT. And let me just go into the application. So supply chain optimization. And here is where you can see what we are going over time, adding like more and more complicated features to the model. And here I'm just going to show you one particular thing that we have here. So in this, it has not been released yet, the videos about lot sizing, but we are implementing lot sizing, and we have 2 ways to implement it: with MP, so automatic reformulations, or old school big M method. Just for you to see a very simple thing that can get complicated. So lot sizing with MP is like this. And by the way, lot sizing is, instead of having a continuous amount of production, you either produce 0 or produce above a certain level. You have a minimum amount of production. With AMPL's automatic reformulations, you can really adjust this. So either production is 0 or the production is greater or equal than minimum lot size. Let me go up here and let me show you just what will be big M method for this. So here we have the same, but using big M method. And of course, the reformulations that we apply, they might end up going to the solver as big M method. That happens especially with the open source solvers. But often there are better ways to transform and linearize these expressions and to achieve better performance. So this is one of the big benefits of really using these high-level modeling constructs, because it is not only very easy to make mistakes when doing something like this, it is also very easy to write an inefficient reformulation using big M. And this is supply chain. Now, and of course, like I mentioned in the beginning, that is our case study where impacts can be quite massive. So another one, logistics. In here, I'm going to focus mostly on airlines, just to show you another example that we have here. And this does not apply only to airlines, like lots of scheduling problems. One of the big issues with scheduling is the issue with preferences. So often scheduling models are not really implemented in practice because they generate solutions that then they make nobody happy. Like people are used to certain characteristics, like they want to work on like preferably on mornings or in afternoons and so on. So they have like several types of preferences that need to be incorporated in the models. And often it is hard to model them, and because they can require some logic and so on. Here we have a model for Aircrew training scheduling with seniority constraints. So in this case, so there are, let's say, 10,000 crew members with different seniority levels and preferences and availabilities. And we want to optimize, to produce a training schedule that manages to satisfy not only the fact that they have certain deadlines for training, but also the preferences. So in case there are multiple solutions that still satisfy deadlines, the people with higher seniority should have precedence in terms of choosing the best option for them. The way we do it is here is using hierarchical multi-objectives. So this is also another interesting thing that MP does. It's not just about automatic reformulations, it's also enhancing solvers. So not every solver has access to hierarchical multi-objectives, but with MP they have. So we emulate these hierarchical objectives for solvers that don't support it. And in particular, for instance, even in solvers that support it, sometimes there are limitations. For instance, Gurobi does not support hierarchical multi-objectives with objectives that are not linear. So if you have non-linear expressions there, you cannot do it. So we allow all of that to be done. And this is how we do it. So by solving hierarchical multi-objectives, we can satisfy as first objective for the people with higher seniority, then the second level, and so on. And this is a way to achieve a good solution. This is a new approach to solve this model. This is a second attempt to something that was presented in a paper, but in the paper, it was presented using constraints, essentially enforcing dominance rules as constraints, making the model way harder. With this approach, we can make the model a lot cleaner, and then just handle the precedences as multi-objectives. So if you are already maximizing the preference for a certain rank, then it's already optimal. You fix that preference level, then you go to the following rank and optimize, and you keep doing that until you optimize for every role. So we have supply chain, we have airlines, where the entire business depends on it. And now, where is really the big impact? Big impact is really finance, is where this starts to getting interesting. There are many types of problems that people can, that people need to solve every day in finance. So the finance companies, they have very big teams that their entire life is to every day trying to come up with better and better models, better data preprocessing techniques, and so on, so that they can beat the market and essentially achieve better returns. We have some examples. In fact, we had a quant doing an internship with us. So we have some very realistic stuff on Collab. So in case you are interested, you can check it there. And one thing about why we are putting all this content on Colab, we have in fact, just on Colab, we have 100 notebooks. We also have Mobook with around 50 notebooks. So we have a lot of Jupyter notebooks out there with content, and the AI tools, they are picking it up. So for instance, here you can see DeepSeek using the fact that they can do, if you have a portfolio optimization problem and you have a minimum weight, either the weight is 0 or the weight is greater or equal than a minimum weight. So it's a kind of lot sizing constraint. And they know that they can just do it in AMPL. I did not even mention it to DeepSeek. It was just out of the box DeepSeek, and I just asked it, okay, write me a tracking error minimization model in AMPL. Let me go into the application. Okay, here it is. So tracking error. So in fact, the main problem that we see really being solved in practice is not like Markowitz. Everybody talks about Markowitz, but in Markowitz, there is one thing, that is the expected returns is super hard to figure out. And if you have the wrong expected returns, you can easily lead the model to optimize in a very wrong way. So one thing that often works a lot better is tracking error. And how does it work? In tracking error, we are trying to follow a benchmark, because in fact, everybody is going to always be compared against a benchmark. So in the US, everybody is being compared against S&P 500. So you want to have a portfolio that is going to somehow follow that benchmark, but is going to beat it. So this is the model. So we have the weights on a benchmark. So depending on how big are these assets on the S&P 500 benchmark, they are going to have a different weight. And this is what goes here. And instead of minimizing the variance of our portfolio, we are minimizing the variance of the difference between the weights in our portfolio and the benchmark weights. This is the tracking error squared being minimized. Another thing that we can do using hierarchical multi-objectives will then have from the portfolios that minimize this, then also minimize the variance. But that is not always needed. Another thing, fully invested, position count, here using the count operator. This is also another thing that DeepSeek knew how to write and knew that it will be valid in AMPL. The minimum weight for 0 and turnover, because you are often like rebalancing portfolios. So you don't want to keep changing everything over and over again. You want to introduce some limits in terms of how much you are going to sell and buy again every time you want to rebalance the portfolio using new data. So here we have the weights for S&P 500. Here we have the companies. We are picking the top 100 companies. And here we have the optimal portfolio using 10 stocks. So we are trying to pick just 10 assets and follow the benchmark. The benchmark is the blue line. The portfolio built is the green line. And as you can see, it is even beating the benchmark. But in fact, in this model, we are not introducing anything to really like any additional information to beat the market, but it is managing to do it with some luck. In practice, the main difference, this is very close to a real model. The main difference is that you will introduce here additional information so that you are not only following the benchmark, but you are beating it based on some knowledge that you have, some experience that you have in terms of, okay, I believe this stock is overpriced now. The model is going too much into it. You can introduce that type of information in here so that the model makes a smarter decision that's not just misled by the fact, okay, there was a certain stock that was just going up very, very fast over last year, but that, okay, what happened last year is not going to be happening in the future. So you need to penalize that somehow. And that's then how you make these models more robust and manage to then beat the benchmarks, or not only beat benchmarks, you might also be just interested in minimizing the down risk. So in case something bad happens, like you see here, you might just want to have a portfolio that is safer. And here you can see, so this simple model, you can see here 5x returns. So you start with 1 million in a few years. So we are training with data from 2021. So we are splitting the train test year, and you can see the portfolio following. And the year it was above 5x from the original investment. So it can generate quite a bit of money, but is still far from the biggest application. That is the one that I'm going to be talking now. So energy. So energy really optimization is core. So everything, every grid out there, it really needs optimization running constantly. So Hitachi, they have a program called Grid View, and is used at several ISOs, for instance, like the New York Independent System Operator, Aircrew. So the entire electric grids in New York and Texas, they are completely controlled by AMPL models that are optimizing the grid in real time, essentially picking which generators are going to be running tomorrow. That type of decision is being made with AMPL. So that is one way where optimization can have significant impact. And we have examples on Colab for optimal power flow, unit commitment, and so on. The type of problems that you are going to be, that you need to do if you are a producer or if you are an electric grid. But now this interesting graph here is how about the electricity demand over the day, and essentially, in fact, the net demand. So once you take in consideration the renewables that can provide a lot of energy that really needs to be consumed instantaneously, you get these net demand curves that can have a lot of variance. So there is quite a bit of uncertainty in terms of weather conditions and so on. And that is going to have a very significant impact in terms of energy prices. And this is the key application where optimization does not generate millions, but generates billions. Because imagine if, for instance, for tomorrow, people are expecting that in Germany, electricity prices are going to be costing 38 euros. If you have a model that tells you that for sure they are going to be using at a certain point in the day the least efficient gas power plant that they have, and that the cost is going to be, let's say, 300 euros. And if they are selling it at that moment at this price, you buy a lot. And then tomorrow, if your model is correct, you sell at the price that it is at, and you make a lot of money. That's why predicting these prices is important. And one of the things that can really affect them is the true demand. So the net demand after you take in consideration renewables. Another factor is which power plants are working, which power plants are under maintenance. And that is the type of information that you can include in your scenarios. You run a model with lots and lots of scenarios, and you get the energy prices. Just to show you a very simple model, as this is a quite complicated application, like the true application is quite complicated. I'm going to show you just a very simple model. So this is called locational marginal pricing. And essentially what you are trying to do, you are trying to minimize the generation cost. So you have a set of nodes. You have a generation cost in each node, and you are trying to minimize the total cost. Also in each node, you have generation and you have transfer. So you can receive electricity or you can send electricity. And what is left is to meet the demand. Also, you have line capacities. So another thing that can also affect the prices. And where do you get the electricity prices? This is a very interesting thing about optimization, is that often nobody may, like when talking about dual values, I think I had never seen really an application that made so much sense for duality. Where are the prices? The prices are the dual values of these constraints. Because what does it mean to change the right-hand side by 1 unit? That is the impact in the objective value. So essentially, how much is 1 unit of electricity costing in the optimal solution at that point? So, and you get that for each of the nodes. So on each of the locations, so for each of these locations, you can get a cost just based on these dual values for a certain scenario. Of course, the real model is way more complicated. You need to model like hydropower plants with quite a bit of detail. Then you have pump storage. You have like nuclear gas power plants. There are lots and lots of details that get into these models. But once you have a model for that, you have something to generate scenarios. So you have some people that are like studying because not all information is public. So you need to really have people that are going to really be trying to figure out, okay, what is the efficiency of each of the gas power plants in Germany? That kind of stuff you need to have. But once you have that and you have this model well calibrated, you have something that is going to just really be generating money for you. And the type of companies that do this, they are companies just doing commodities trading. You don't see them like buying or selling anything to the public, because the only thing that they do is really hiring very smart people. So very big teams where everybody is doing optimization every day with the objective of really figuring out how to beat the markets, how to know information that nobody else knows up front by writing optimization models and running lots and lots of simulations to know what is going to happen in the future. In here, there is really a lot more power for optimization than really, for instance, like the true finance applications. Because really in finance, there is a lot in terms of public opinion that is going to really move the markets. In here, there is really a lot of inside knowledge that you might put in there. It's not like the power plants are going to just be deciding to sell or buy energy at very weird prices. They will try to bid as low as possible, because the way that the market works is the lower you bid, the bigger the amount of power that is going to be assigned to you. So it's very predictable. You just need to assume, okay, everybody is going to be doing that well, and you have a model that is going to give you the energy prices. One thing related to this, so this implies solving lots and lots of scenarios of these big and complicated models. And in fact, it's not a MIP or anything, it's just a pure LP. And we don't even care about the primal solution. We just care about these duals that give us the prices. And one interesting thing is that the NVIDIA created this solver, QOpt, and we have been testing it. And the main application we found for it was in fact this. So essentially just throwing these models at this solver, because it doesn't really not give you a vertex of like a simplex solution. It gives you an iterative solution, both primal and dual, not necessarily optimal, but close enough to it. And that information, if the dual values, they are close enough to reality, as everything here is an approximation, that's all you need. And it just needs to be fast. So these models, they are quite terrible numerically, very hard for the solvers. And in here, in some instances, we got like a 50x speed up. So instead of taking 90 seconds to solve the model, it was taking us just 2 seconds to solve it. So it can be quite fast. The only thing here is that you need to be sure that these dual values that you are getting are accurate. So, and another thing, why AMPL is used so much for this. So like I mentioned, this model could then, let's say, European grid, solving in 2 seconds. You also have the model build time that you need to do for every scenario. AMPL can be around like 100x times faster than other modeling tools. Recently, we translated the model for Europe for electricity price prediction, and it was taking 5 minutes just to generate the model in pulp. After rewriting in AMPL, the model build time went down to less than 1 second. So that is, in fact, 300x speed up in terms of model building. And you combine that with a solver that can then be solving each scenario in 1-2 seconds, and you get a very fast way to run tons and tons of scenarios and get good confidence in terms of electricity price distributions. And yeah, so just to finalize, if you are passionate about solving cutting-edge optimization problems, we are hiring, in particular, people interested in finance and energy, in particular commodities trading. And just some resources. So Streamlit is the main place where I keep adding these applications that are as realistic as I can make them without really sharing anything that could get me in trouble. Then we have Movebook, we have Collab, and here we have modeling guide for MP. And that's it. You can try AMPL at try.ampl.com.
Thank you so much, Bob and Filipe. So we do have a couple questions. So starting with the first one, is there an API in AMPL for communicating with SQL databases?
Yes. So AMPL can already communicate directly with SQL databases. Another way is from Python to do that, but AMPL itself on its own can communicate directly with all kinds of SQL databases, as long as they have, for instance, ODBC. And not only that, also other types of things that people call database, like even Excel, the spreadsheet, so you can communicate with it directly.
Wonderful. All right, the next one. In many real-world scenarios, especially in commodities trading or energy markets, forecasting plays a key role before optimization. Have you seen AMPL models integrated with time series pipelines like ARIMA or Profit, especially for dynamic re-optimization as new data arrives?
Yes. So that is a very important thing. So like the people that work at like these companies doing commodities trading and getting all this value out of optimization, they have a lot of people working just on the data itself, because even in the model, you can also introduce some concepts that are going to give you like some freedom. So that you also don't optimize too much in the wrong direction. Like I mentioned in the portfolio optimization, if your model really depends a lot on expected returns, they are super hard to predict. You might do a very wrong choice. But yeah, in terms of commodities trading, forecasting using models like ARIMA and Profit and so on, that is a very common way of doing things. And then from these models, often what you get is not just the prediction, you also get a kind of confidence interval. And then you generate a bunch of scenarios from these confidence intervals.
All right, our next question. Given the risks of numerical instability and hidden solver quirks, especially with GPU accelerated or approximate dual solvers like QOpt, what formal checks or safeguards does AMPL apply to ensure the correctness and stability of its automated model reformulations before solver execution?
So in terms of that, we do solution validation. One thing that happens, for instance, in solvers like QOpt and so on, there are going to be issues. So they are quite loose in terms of tolerances. If someone is really relying on a solver like that, they also need to put some knowledge from what they know to really validate, okay, does this solution really make sense, or is there something that seems odd? Because there is a lot that is being relaxed in these models. We are solving an LP for something that the true problem is a MIP. So we are relaxing so much. We are also using lots of information that is not necessarily true because it's not publicly available. So there needs to also be some validation step from the users themselves. So it's not just data preprocessing, optimization, there is also solution validation that is quite important to also be done, and on a problem by problem basis. It's not something that we really can do on our own, because we know that these solvers, they have tolerances. And in fact, when you are using them, you have an option where you are really setting the tolerances, and you need to, and if you really reduce tolerances a lot, they get very inefficient. So for them to be efficient, you need to let them loose. So it's then up to the user to control that, because otherwise we will just say, yeah, this is really violating lots of tolerances. Proceed at your own risk.
Awesome, thank you. All right, the next one. How does AMPL compare to GAMS in speed?
So in terms of speed, we have never really compared against GAMS, but I will say it will be very hard to beat us when we generate a model for the European grid in less than 1 second. So that is one of the key things that we know. Another thing is in terms of the model quality being sent to the solvers. That is one thing where we know that a company using GAMS for modeling, they were struggling a lot more in terms of solving the problems than they will be using AMPL. And I would expect the reason for that will be lots of big M's reformulated by N. So it's not just really model building where we are extremely fast is also the quality of the models being sent to the solver that can also have a performance impact. So overall, I will say way faster if you really take in consideration the two aspects.
Awesome. So I know it's one. We have two more questions. Do you guys have time for those?
Yeah.
All right. So the next one, are you aware of any attempts to use GPU accelerated linear solver with IPOPT, IPOPT?
No, in the nonlinear space, I believe nobody has tried anything yet. Eventually in the future, we might start seeing since there is some interest there. But so far, I believe nobody has tried that. Because this also seems a very recent approach, like NVIDIA started doing this a few years ago. Then it was also COP that they created QPDLP. So this is very recent stuff happening right now. Yeah, but in the future, that might be something that we may also see people trying to do something in terms of nonlinear problems.
All right, last question. What's the best NLP solver in your opinion?
One thing is that it really feels like it depends a lot on the problem. Bob is the person with most experience there, but my impression is that it really depends a lot on the type of problem that you are solving. Bob, can you provide more insight there?
Daniel, are you able to provide any more insight or context there?
There, yeah. So with nonlinear solvers, it's particularly important to run tests. Not only does each one have certain advantages for certain kinds of problems, but there are several very different kinds of algorithms that are implemented in these solvers, and so the algorithm that's in one solver may not be appropriate for the kind of problem you're having. Maybe your problem has relatively few variables and lots of constraints, and they're all nonlinear, and that you need a solver that handles that. And a different solver might work if you have mostly linear constraints and just a few nonlinearities. So I'd say that I would hesitate to recommend one nonlinear solver is the best. The best thing to do is to try 5 of them and see which one works best on your problem. And some sort of modeling language is good for that, because you basically you can take the same model and send it to all 5 of them and see what results you get.
And Daniel added in ACOPF as an example.
Yeah.
All
Okay.
right. That was the last of our questions. Thank you so much to Bob and Filipe. And thank you everyone for joining us today. So on behalf of AMPL and Informs, Bob and Filipe would like to thank you for joining us today and let you know that a recording of this webinar will be available on our YouTube channel very soon. And I will follow up with an email with that link when it is ready. Any thoughts, final thoughts from you, Bob or Filipe?
No, thank you all for being here, and feel free to reach out if you are looking for solving some of these very performance critical optimization problems where the impacts can be quite massive. We are quite experienced with that, and we have a support team that can really help you to really take full advantage of the solvers for maximum performance.
Wonderful. Thank you all so much, and we'll talk soon.
Right.
Have a great day, everyone.
Good day.